What's up, everybody, and welcome back from spring break, the most unique spring break you may ever have in your life. I know it was for me. It did feel like a break. I did no schoolwork, I'll admit that, and now we're back to it. Test number 4 material. What is test number 4 about? Test number 4 is all about, let me close this out here so you don't have to see my mug. Test number 4 is all about estimating means and estimating standard deviations and estimating proportions, and then we get into something called hypothesis testing, the second half of test number 4. So estimated means, what does this even mean? Well, let's read this sentence right here. It says, to estimate population parameters such as mu and sigma squared, we use sample statistics. All right, quick breakdown of that. Mu is the population mean. Sigma squared is the population variance. Don't forget those things, but the key word there is population. Two factors which affect sample statistics and their corresponding confidence intervals are sample size and types of sampling design. All right, so what does all this mean right here? Well, as a statistician, it's almost as if this is a mystery. All right, we are solving mysteries this entire lesson. The mystery is, what is, oh, let me do that. What is mu. There we go, good echo effect right there. The population mean. The only way to truly find mu, the population mean, is to gather every single person or thing from a population. It's nearly impossible to do. We do something called a census every year. We still don't collect everything. I'm sorry, every 10 years, I apologize. We're doing it right now. It's happening as I do this lesson. All right, there are emails being sent out, letters being mailed out, trying to gather census information. However, we never truly collect it all. So what's the best that we can do? The best we can do is collect a bunch of samples. All right, what affects the accuracy of those samples? Two things. One is the sample size, and two is the type of sampling design. So in this class, we are going to make a statement here, and this is almost a well-duh statement, but it's needs to be said. The larger the sample size, the more accurate the estimate. Kind of makes sense. If you take a bigger sample, you're going to get a more accurate representation of the entire population. Okay. However, this statement comes with an asterisk, and that asterisk is the next sentence. These formulas will assume that a random sample has been taken. Okay. You could take an absolutely massive sample, but if it's not random, it's nothing. All right. History has taught us that biased samples produce bogus results. And so, no, bogus, not accurate results. There we go. Better way to say it. All right. Types of sampling design. What are ways to sample from a population? Well, I'm going to go over it right here on the second half of this page. One of the most simple ways is a simple random sample. Number one, a simple random sample. Each number or person has an equal probability of being selected. So let's just say that all of the students from our school, and by the way, there are roughly 2,000 students in our school, all right, receive a number, 1 through 2,000. Put them on 2,000 ping pong balls. That's going to take up a lot of space. Put them in a huge wheel, and then pull out 50 ping pong balls, or 80, it says right there. Every single person in the school has an equal chance of being selected. All right. So what about a stratified sample? All right, so stratified sample says break the group into many strata and randomly select from each strata. Strata is just a fancy way of saying a group, subgroup. Okay, so let's say that our strata are 9th, 10th, and 11th, and 12th graders. Suppose I want to get an indication of how people during this unique time. However, I don't just want to sample seniors, I want to sample every grade. All right, and so how could we find this out? We sample maybe 10 freshmen at random, 10 sophomores at random, 10 juniors and 10 seniors. And then we find out what each grade feels about homework, or how each grade feels about homework. 3, systematic sample. Not necessarily random, but not random either, using double negative. Select every nth person or number. Companies use this a lot. Maybe selecting every 10th person alphabetically and choosing them to receive a survey. Again, maybe not so much random, but it is not biased at the same time. Last but not least, a cluster sample. Break the population into a number of clusters, randomly select a few clusters, and sample everyone within those clusters. So let's say that it says homeroom is a cluster. So out of maybe the 50 homerooms from the first day of school, pick 10 of them at random and then sample everyone within those clusters. I don't know if you noticed it, but 2 and 4 seem oddly similar. They are similar. They are both breaking the population into subgroups, either strata or clusters. The difference is a stratified sample samples a few randomly from every single strata. Cluster sampling just samples a few clusters, but samples every single person within those clusters. And I just want to talk about cluster sampling for a second. I was, I don't want to say a victim, but a participant in cluster sampling. If you've ever been curious about how TV ratings happen, you ever see, like last night, the Emmys had a 5 share. That means 5% of the population was watching the Emmys. How do they know that? I mean, we have boxes above our TVs, most of us now, but we didn't at all times. So here's how it actually happens. People receive letters, and there are 2 companies. One is the Nielsen company, and another is the Arbitron company. And the reason I have this information is because I received letters from both companies asking if I would participate in having my box be watched by Big Brother. And they tried to entice me, get this, with a crisp dollar bill. There was a dollar bill folded up in this envelope asking if I would participate in the Nielsen ratings or the Arbitron ratings to tell how many people are watching certain shows. So this stuff actually that I'm showing you gets used, and it's cluster sampling. They do it by neighborhood. So my entire neighborhood was canvassed, and everyone in my neighborhood received that letter, and you decided whether you wanted to participate or not. All right, bye. So this stuff actually does happen. Let's move along. All right, so now let's go to the next page. The sample mean, X bar, is the best point estimate of the population mean mu. What does that mean? Well, I told you that today's lesson is like a mystery. Mu, the population mean, is a mystery. Guess what, everyone? We will never, ever quite know what the mean of an entire large population is. We'll never know, especially a population as large as our nation. Okay? The best guess we can ever make is by taking a good sample or many samples and using that sample as our best guess. Instead of calling it a best guess, though, I call it a best point estimate. So mu is a mystery that is never going to be solved, and X bar is the best guess to that mystery. So what do statisticians do? All right, I'm going to get visual again. Statisticians say this. There will be no statistician so pompous to say, my sample mean is so accurate that this is the exact representation of the population mean. You'll never hear a statistician say that. What you will hear is this. Listen, my sample mean is right here. I'm not positive that that is where the population mean is, but I'm fairly confident that the true population mean is somewhere between here and here. Do you see what I did? I built an interval with my hands. I kept the sample mean in the middle, and then I added and I subtracted a little bit from the sample mean. Apologies, I don't know which way is adding and subtracting because it's backwards or it's not backwards. You get what I'm talking about. All right, let me get back off screen here. To construct a confidence interval, that interval that I just made with my hands is called a confidence interval. We must look at the sampling distribution of means. All right, and we learned from, oh, sorry, I don't know why that just did that. We learned from the central limit theorem that the distribution of sample means is normally distributed. And so what does this picture represent? Well, these barriers right here are there for a reason. We're trying to find the mystery population mean, mu. Mu might be here. Mu might be here. Mu might be here, but guess what? Mu also might be down here. It's less likely that mu is over here in the tails, though. How do we know that? Because the distribution is normally distributed, and most likely it's going to be somewhere right here in this center. What's the probability that it's somewhere in that center? 1 minus alpha. That fishy looking symbol is alpha. Okay, so if the probability that the population mean is somewhere in this big unshaded area is 1 minus alpha, then the probability that it is in either of these two shaded tails is alpha. And every curve is symmetrical. Every normal curve is symmetrical. So I'm going to split alpha in half. So half of alpha, or alpha over 2, is on the right tail here, shaded. And half of the alpha, or alpha over 2, is in the left tail, shaded. These barriers are represented by the z-scores that separate the unshaded area from the shaded areas. So this is the positive z-score at that alpha over 2 level. It's not times alpha over 2, it's just at the alpha over 2 level. And this is the negative z-score at the alpha over 2 level. I know this seems like it's all Greek to you. I'm here all week, folks. I know. Yes, these are Greek letters. But just go with it right here. Where did I come up with 1 minus alpha? I just created the variable alpha. I could have said x, said alpha. All right. So there are two very popular values for alpha. And the two most popular values for alpha, and by the way, not the only values by any means. As a matter of fact, your homework will use many different values of alpha. The two most common values for alpha are 0.05 and alpha 0.01. If alpha is 0.05, if I take 0.05 and I split it in half, I get alpha over 2. 0.05 divided by 2 is 0.025. And 0.025 over here. But remember, how do I use a z-table backwards? How do I look up a z-table backwards to find a particular z-score? Well, first I split the graph in half, which is 0.5. So if I do 0.5 minus 0.025, I get 0.4750. And over here, 0.4750. These are the two areas that I am going to, or the one area that I'm going to look up backwards on my z-table. I have my z-table handy. Let me get it out for you. Let's find the closest area to 0.4750. I believe I don't have to look up the closest to. It's exactly right there. So that's 1.9. And then what is it up here? 0.06. So the z-score that produces an area of 0.4750 is 1.96. There it is. And negative 1.96. So the z-score at the alpha over 2 or 0.05 over 2 level is 1.96. That might seem like a random number. Get used to it. 1.96 is going to be like butter. It's going to be so common to you in your statistical language. The other common alpha level is 0.01. And if you take 0.01 and split 0.01 in half, you get 0.005 and 0.005, which leaves 0.4950 here from the center out to the mean. So let's look up 0.4950 backwards on our z-table. So 0.4949, ooh, look at this, 0.4949 and 0.4951. It is directly in between two areas right there, the one we're looking for, 0.4950. So that's 2.57 and 2.58. So what do you do if you have an area you're looking for that's directly smack dab in between two areas on the z-table? You average the z-score. Instead of saying 2.57 or 2.58, we say, wait for it, here it is right up here, 2.575. I don't know if anybody saw that before I circled it. It's one of two special z-scores that are rounded to 3 places. So the z-score that is associated with alpha 0.01 is 2.575. All right, let that stick in your craniums, everybody. The z-score associated with alpha 0.05 is 1.96. The z-score associated with alpha 0.01 is 2.575. I'm going to stop this recording right now, and I'm going to start a new video because this one's starting to get long.